students. Now moving towards the next lecture of unit number 2, that is a baseband digital transmission. Let's have a quick revision that what we have studied in our previous lecture. In our previous lecture, we have seen that what is conversion. Then we have seen the types of conversion, that is analog to digital conversion, digital to analog conversion, analog to analog conversion, and digital to digital conversion. After that, we have seen line codes. Line codes, basically, it is a type of digital to digital conversion. That is how we are going to convert a digital data into digital signals. Then we have seen the various types of line codes as like your unipolar. Then we have seen polar. Then we have seen bipolar. And we have seen how to draw the waveforms. What are the advantages or what could be the disadvantages of it. We have also seen the properties of line codes, then characteristic of line codes, and at the end we have seen the comparison of all those line codes. Now moving towards our today's lecture, our topic we are going to start with that is a power spectral density of line codes. Well, power spectral density of line codes, also we can tell PSD of line codes. Basically, it is used to measure the power content of the signal in frequency domain. As you have already studied in your second year of engineering, that is in signal and systems, that how to find the PSD, how to find the power spectral density of any signal. So first step is to find the Fourier transform of the pulse. It is say it is x of f. Then we need to find the autocorrelation of the suppose it is a unipolar signal, it is there, then it could be r of tau, and calculation then PSD by using based on both Fourier transform and autocorrelation. So it means it is a Fourier transform of autocorrelation function of any input random process, that is x of tau. Now this is the figure of your PSD of line codes. So basically, if you are going to see on the screen that there are different types of line codes are there. Focus on this one, which is given by curve A. This curve A, it is nothing but your unipolar NRZ, that is non-return to 0. This is a graph of polar NRZ. This is bipolar NRZ, and this is your Manchester line code. So basically, power spectra, it is nothing but a graph of power spectral density plotted on y-axis against the frequency on your x-axis. So it is going to give you the distribution of power of different frequency components. So there are four important line codes, the power spectra of these four important line codes. So if you will see that curve A, that is called a unipolar NRZ, both the power spectral density and the frequency are normalized, and most of the power of this NRZ unipolar format is concentrated between DC and bitrate of the input data. Next, moving towards the curve B. So curve B, it is a power spectra of polar NRZ. So it is going to show the normalized power spectra of this format. Most of the power, it lies in the main lobe. This is a main lobe of your sinc function. Because why we are using sinc function, instead of transmitting a rectangular pulse, in order to reduce the ISI effect 0, it is better to transmit sinc function. So what is ISI? It is there in the lecture. So today we are also going to discuss ISI. So the main lobe basically it extends up to this rate of 1 by t. Now the next curve, it is called a curve C. It is a bipolar NRZ. So it is going to show you the normalized power spectra for this bipolar NRZ, or we also called as AMI, that is alternate mark inversion. So it can be seen that all the power it is lies inside the bandwidth equal to this 1 by T. And however, the spectral content of this NRZ bipolar format is relatively, very small, around this zero frequency. And next curve, it is called what? Manchester line codes. So in this, what? Most of the power it is lies in the bandwidth equal to what? 1 by the 2 by T, which is twice the bandwidth of what? Unipolar and bipolar NRZ. So basically this Manchester, if this signal, Manchester signal, it is transmitted through an ideal low pass filter with a cutoff frequency 2 FB, then about 95% of power it would be transmitted. But if this cutoff frequency it is reduced to, that is FB, now it is what? Almost twice FB. So 95% of power it is going to transmit it. But look at on the screen, if this cutoff frequency it has been reduced from 2F to 1F, then only 70% of the power it would be passed. But over here the bandwidth requirement it is twice of F, which is the double the bandwidth of what? NRZ signal. Now we are going to see the individual power spectra of unipolar this line codes. So first is what? NRZ unipolar. So in this one it is represented, see, it is the PSD, power spectral density of your unipolar NRZ unipolar. So it is given by the function equation a square by t upon 4 sin square of f of t plus a square by 4 into del f. Basically in your examination there is no need to find the individual power spectral density of each line codes. So you can just see from this equation, basically A it is nothing but your what? Amplitude, that, or we can say it is a voltage. T it is what? It is a symbol duration. And del f it is what? Unit impulse at f equal to 0 in the frequency domain. And this is a sinc function, because as you are going to see the curve, all the curve it is in the form of your sinc function. Now similarly, this is a power spectra of NRZ unipolar. Next, the power spectra of NRZ polar format. So you can see that equation, that is a square into t sin square of f of t. So most of the power it is lies in the main lobe of this sinc shape curve. Next is your NRZ bipolar, which is also called as AMI format. So this is the equation, that is PSD of AMI is equal to a square into t sin square of ft into sine square of pi ft, and this is the Manchester format. And this is the equation for this your Manchester format, that is a square into t sin square f of t by f of t ft by 2 into sine square of pi ft by 2. So you can see that if its bandwidth it is the cutoff frequency is 2f of ideal low pass filter, then 95% of power it would be transmitted. But if the cutoff frequency it reduced to f, then only 70% power is passed. Now moving towards the next topic, that is called intersymbol interference, that I told that basically instead of transmitting your unit pulse or rectangular pulse, if we are going to transmit the information in the form of sync pulse, then it is possible to reduce this intersymbol interference. But before that, we are going to see that what is intersymbol interference. Now, in a communication system, when the data is being transmitted in the form of pulses, the output produced at the receiver due to other bits or symbols, it interferes with the output produced by the desired bit. So, ISI intersymbol interference, it arises due to what? Imperfection in the overall frequency response of the system. Also, we can get this ISI, when a short pulse of duration t seconds is transmitted through a band limited system, then the frequency components contained in the input pulses are differentially attenuated, or more importantly, we can say differentially delayed by the system. Due to this, the pulse appearing at the output of the system, it would be dispersed over an interval which is longer than t seconds, because rectangular pulse, it has a duration of t second, but due to this dispersion, what is going to be happen? This pulse, it is going to disperse longer than that t second. So due to this dispersion of the symbols, each of duration t, it is going to interfere with each other, with other symbols when transmitted over the communication channel, and this will result in ISI, that is intersymbol interference. So you can see on the graph on this figure that how the ISI it is going to take place. You can see on the screen, suppose the data is 1 0 0 0. So we are assuming for bit 1 we are going to transmit a 1 pulse, and for rest it is what? 0. So the response of this one, it is like this one. See, it means it is going to extend the duration of this t. This is your t, and this is a received waveform of it. Now, if the data, suppose it is 1 0 1 1, it is there, then this is the response of this first pulse, and then after that it is a 0, it is there. But you are going to see this pulse, it is going to cross over the duration of its own. This is t, and it is going to extend from either a direction of this duration. So what is going to be happen? Next bit, it is what? 1. So over here again, this is a response of this third pulse, it is there. So you can see on the figure that how they are going to interfere with each other. Due to this, what is going to be happen? The information, it could be lost. So due to this, pulse appearing at the output, it is going to be dispersed over an interval which is longer than this t second, and due to this dispersion, this symbols, each of duration t, they are going to interfere with each other, and when they transmitted, and see on this manner, the receiver, it is going to recognize this your signal. So this is known as what? Intersymbol interference. Now, what are the effects of your intersymbol interference? So the presence of ISI, it is going to introduce error in the decision at the receiver output, because on this graph you can see how it is going to recognize this a received signal in a wrong manner. After that, since the receiver, it can make an error in deciding whether it has received a logic 1 or logic 0, because if the bit 0 it is transmitted and bit 1 it has been dispersed along its duration, then what is going to be happen? The receiver, it can make logic 1 instead of logic 0. So this problem, it would also happen in your ISI. Next, Due to this, the absence of ISI or noise, the transmitted bit, it can be easily decoded correctly at the receiver. Now, what are the main causes of ISI? The main causes of ISI, first is what? Multipath propagation. Now, what is this multipath propagation? Basically, multipath propagation in which a wireless signal from a transmitter, it reaches the receiver via multiple paths. So, the causes of this, includes reflection. Reflection, it means the signal may bounce off from the building, or the refraction, or some atmospheric effects. So, due to which the various paths can be of different lengths, and this results in the different version of the signal arriving at the receiver at different times. So these delays, it means that part or all of the given symbol will be spread into the subsequent symbols, and thereby interfering with the correct detection of those symbols. Additionally, the various paths often distorting the amplitude or the phase of the signal, thereby causing further interference with your received signal. Another cause of ISI, it is your non-linear frequency in channels. It means that in the transmission of the signal through a band limited channel in the sense what? Where the frequency response is zero above a certain frequency, as we called it as a cutoff frequency. So passing a signal through such channel, it results in the what? Removal of the frequency components above this cutoff frequency. In addition, components of the frequency below the cutoff frequency may also be attenuated by this channel. So this filtering of the transmitted signal, it is going to affect the shape of the pulse that arrives at the receiver. And the effects of filtering a rectangular pulse not only change the shape of the pulse within the first symbol period, but it also spreads out over the subsequent symbol periods. So when a message is transmitted through such channel, the spread pulse of each individual symbol will interfere with what? Following symbols. So these are the main causes of ISI. Now what are the remedy to reduce the ISI? It has been proved that the function which produces a zero intersymbol interference is what? Your sync function. So hence, instead of a rectangular pulse, if we are going to transmit a sync pulse, then ISI, it could be reduced, and this is called Nyquist pulse shaping. Further, we know that the Fourier transform of a sync pulse is what? Rectangular function. Hence, to preserve all the frequency components and the frequency response of the filter, it must be exactly flat in the pass band and zero in the attenuation band. So ISI, basically it is unwanted and should be completely eliminated to get a clean output. Now, moving towards the next topic, that is called what? I diagram or I pattern. So what is this I pattern? Basically, an effective way to study the effects of ISI, it is what? I pattern. And the name I pattern, why we have given the name I? Because it has a resemblance to the human eye for your binary waves. So the interior region of the I pattern is called I opening, and here it is the figure of your I pattern. Basically, this I pattern, it is displayed on the screen of your CRO. So the shape, as I already told, it resembles with shape of human eye. Now, the I pattern, basically it is obtained on the CRO interference by applying what? Received signal to the vertical deflection plate, that is a Y plate of CRO, and the sawtooth wave at the transmission symbol rate, that is 1 by T, to the horizontal deflection plates, that is X of plate of CRO. Then the received digital signal and the corresponding oscilloscope display, you can get it on the screen as it is present on the screen. Now the this interior region of this eye pattern is called what? Eye opening. And this eye pattern, basically it provides a great information about the performance of the system. Now the width of this eye opening, it is going to define you the time interval over which the received signal can be sampled without an error due to what? ISI. So the best time for sampling is when the eye is what? Most open, widest. Now the sensitivity of this system, to this timing error is determined by the rate of closure of the eye, as sampling rate is it is varied. So the height of the eye opening at a specified sampling time, it is going to define what your noise margin over this noise. And when the effect of ISI is very severe, the eye, it is what? Completely closed, and it is impossible to avoid errors due to the combined presence of ISI and noise in the system. So if in examination it has been asked, you have to draw this waveform, and see, this is called what? As a jitter, and this is going to tell you the amount of distortion, that is your signal to noise ratio, and this slope, it is going to tell you the sensitivity. Just I told that about the timing error, the smaller the better. Now what is jitter? So jitter is basically what? A short-term variation of the instant of digital signals from its ideal position, which may lead to data errors. So when the effect of ISI increases, the traces from the upper portion to the lower portion of the eye opening, it increases, and eye gets completely closed if this ISI is very high. Now what kind of information we get from the eye? Actually, eye patterns are used to transmit the bit error rate and the signal to noise ratio. Also, the width of the eye opening, it is going to define you the time interval over which the received wave, it can be sampled from the ISI without error from the ISI. The instant of the time when the eye opening is wide, it will be the best time for your sampling, and the rate of the closure of the eye according to the sampling time, it determines how sensitive the system is to the timing error. Also, the height of the eye opening at a specified sampling time, it defines what? The margin over noise, and hence the interpretation of the eye pattern is very, very important consideration. Now moving towards the last topic of this unit, that is scramblers and unscramblers. So basically, what are scrambler? In communication application, sometimes it becomes very essential to transmit the message in such a form that the only desired receiver it should be able to understand, and for this it is needed to perform what? Coding. So scrambling, it is nothing but a coding operation which is applied to the message at the transmitter. So the process of scrambling, what is going to do it? It is going to randomize the bit streams, eliminating the long strings of zeros and ones which might affect the receiver synchronization. So suppose if you have a data 101010, then it may happen the scramble, it means it is going to rearrange the data sequence. So it could be 01 or 1011 like that one. But at the end of the receiver should be able to get the information in the same sequential manner. So why we are going to do it? Basically, the unauthorized user, it should not be able to read the your desired information. So that's why the importance of scramblers it is there. This is the figure on the screen that how the scrambler it is going to looks. See, this is part, it is called a transmitter. This is scrambler and this is your unscrambler it is there. Now first we would see about a scrambler. So this is your binary scrambler it is there. So basically on the screen you can see it is going to use a 4-stage shift register, that is 1, 2, 3 and 4. These are what? Shift registers. With the tap gains, that is we are going to denote it by alpha 1, alpha 2, alpha 3 and alpha 4. Over here this alpha 1 and alpha 2 equal to 0 and alpha 3, alpha 4 we have seen what? 1. And MK, this MK it is nothing but your binary message sequence at the input to the scrambler. Then this has been added to this register output it is there to obtain the scrambled message M dash of K. This M dash of K, it has been fed back to this shift register input. So you can see this is M double dash of K, this is MK and the output is what? M dash of K. So this is nothing but your modulo 2 adder, and output of this modulo 2 adder it has been fed back to this shift register input. Now from this figure we can write the equation that M double dash K, it means the output of this first modulo 2 adder is what? M dash of K minus 3 modulo 2 adder with M dash of K minus 4. So you can write this equation as equation number 1. I expect all the students please write this equation in order to understand your scrambler and unscrambler. Second equation. Now this M dash of K is what? This is the modulo 2 addition of M of K plus M double dash of K. So you can write it M dash K is equal to M of K modulo 2 addition of with M double dash of K, make it as equation number 2. And what is this? M dash K, it is nothing but your scrambled message. Scrambled message in the sense we have changed the bit sequence of it. Now this scrambled version is completely different from the original message M of K. It can't be recovered unless we have a proper unscrambler at the receiver. So here it is your unscrambler shown on the screen. Its structure exactly reverse as compared to the structure of your scrambler. Again you can see on this screen that there are also 4-stage shift register that is there, 1, 2, 3 and 4 with tap gains denoted by alpha, that is alpha 1, alpha 2, alpha 3, alpha 4. Since we have taken alpha 1 and alpha 2 equal to 0 and alpha 3 and alpha 4 equal to 1, the output of these two shift registers it is given to the first modulo 2 adder whose output is denoted by what? M double dash of K. And M dash of K it is nothing but your scrambled message. So the unscramble is used to recover the original message signal M of K from what? This scrambled signal M dash K. Now M of K, it is going to reproduce, it is nothing but your original message signal at the output. So now you can see on the screen how we can write it. this m dash k plus, that is a modulo 2 adder with m double dash k is equal to m of k, right? But this we can write it, since we know m of k is equal to what? M of k plus m double dash of k from equation number 1. So you can substitute the value of this m of k over here. So we have put m of k modulo 2 adder with m double dash of k, which has been modulo 2 added with this m double dash of k, which is make is as equation number 3. Now, as you know that what is modulo 2 adder, if 0 0 it is there, then it means same inputs are there, then the output of modulo 2 adder it is what? 0. If inputs are different, then its output it is 1. So if it is 0 0, then output would be 0. If input would be 0 1, then output of modulo 2 adder it would be 1. And if it is 1 0, then also output would be 1. But last, if both the inputs are 1 1, but they are similar, so the output of modulo 2 adder it would be what? 0. So you can see from this equation 3 that m of k modulo 2 adder with m double dash k plus m double dash k. But as you know this property of this modulo 2 adder, if the both inputs are same, then output it is 0. So we can write it that m dash of k modulo 2 adder with m double dash of k is nothing but your m of k plus this modulo 2 with 0. So this is our what? Final equation, that is m dash k modulo 2 adder with m double dash of k, which is nothing but your m of k. So thus by adding modulo 2 addition, the scrambled signal m dash k with m double dash k, it is possible to obtain the original signal m of k. So it may be noted that due to the identical structure of this shift register at the transmitter and receiver, the same m dash of k for the scrambler as well as for unscrambler, and we will get the same sequence, that is m double dash k for the scrambler as well as unscrambler. So here we are going to finish your scrambler unscrambler. The one more point it is remained in this unit, it is called what? Equalization. Now for reliable communication to be established, we need to have a quality output. So the transmission losses of the channel and other factors which is going to affect the quality of the signal, they need to be treated. So the most occurring loss up till now we have discussed is what? Your ISI, that is intersymbol interference. So to make the signal free from this ISI and to ensure a maximum signal to noise ratio, we need to implement a method called what? Equalization. So the following figure, it is going to show you the equalizer in the receiver portion of the communication system. So the noise and the interferences, which are denoted are likely to occur during this transmission. And this regenerator repeater, it has a equalizer circuit which is going to compensate this transmission losses by what? Shaping the circuit. And hence the equalizer, it is very feasible to get implemented, as this is a block diagram of this of this entire communication system, that how the noise and interference it has been added, where is the location of this digital equalizer which is at the receiver, and we are going to assume the transfer function of the channel, that is called HC of f, and the transfer function of this equalizer HEQ of f. So due to this noise and interference, it is needed to compensate the effect of this noise and interference, we required what? Equalizer. So let HCF be the transfer function of the channel and HEQ of f be the transfer function of the equalizer. Then the overall transfer function of this cascaded connection, is given by what? By multiplying the transfer function of this channel, and the transfer function of equalizer is equal to k into e raised to minus j 2 pi ft. So k, it is nothing but your scaling factor, and t, it is nothing but your constant time delay. So the transfer function of the equalizer is what? Then h eqf is equal to k into e raised to minus I 2 pi ft upon hc of f. What are the types of equalizer? So the types of equalizers, it could be linear equalizer as shown on the screen. It processes the incoming signal with a linear filter. Next, it is your adaptive equalizer. It is typically a linear equalizer which updates the equalizer parameter as it processes the data. The next equalizer, it is turbo equalizer. It applies what? Turbo decoding while treating the channel as a convolutional code. Then Viterbi equalizer, it is also there. It is going to find the optimal solution to this equalization problem and having a goal to minimize the probability of making an error over the entire sequence. So up till now we have studied that what is, interference, it is there. What are the different types of interference, it is there. We have seen that how ISI, it is going to take place, what are the effects of ISI, and how to overcome the effect of this ISI. Then we have seen that how scrambler it is going to work, how unscrambler it is going to work, that what is the use of scrambler, that just to change the data sequence so that the unauthorized user, it should not read that message. After that, we have seen the way how we are going to study the ISI, that is of I pattern, or we said it, call it as I diagram. And then we have seen the equalizers, that why equalizers at the receiver in digital communication, it is required in order to compensate the effect of noise and interference. So here it is the end of unit number 2. These are the assignment that you have to solve it and submit it. So please note it down, this assignment. For any feedback or any query, there is my email address on the screen. So thank you very much guys. It's all about our today's lecture.